Hello Year 9, for those of you who may not have been taught by me, my name is Miss Boots and I'm just going to be giving you some feedback from the Google Classroom quiz that you completed and some of the questions that some of you guys found a little bit trickier. So let's carry on. Firstly, we're going to be talking about how to calculate protons, neutrons and electrons. So firstly, we've got our little picture of the atom here with our protons and neutrons in the nucleus in the middle and the electrons going around the outer electron shells. Then we have our very important table of the charge and the mass of the atomic particles. So the protons are positively charged. You can remember that as P for positive or pro as being for something or feeling positive about something. Neutron have no charge. They are neutrally charged. That's the way to remember that. And then by process of elimination, our electrons are going to be our negatively charged atomic particle because we need something to balance out those positive protons. Then we're talking about mass, and this is measured in atomic units. So we have protons, which are a mass of 1, neutrons, which are also mass of 1, and then electrons have a mass that can either be written as just 0 or no mass, but they do weigh something. It's just a really, really tiny amount, which is even 1/2000 of an atomic unit. Then when we're talking about calculating how many protons, neutrons and electrons are in a particular element, there are two numbers to bear in mind. First number that we need to take into account is the proton number. And as the name suggests, that indicates the number of protons an element has. Next, that can also be called the atomic number because the number of protons indicates what type of atom that atom is. So any atom that has 8 protons is going to be an atom of oxygen, and so forth. That's never going to change. The second number is the mass number, and you can remember that as being the massive number, the bigger number, because sometimes it's on the top, sometimes it's on the bottom, sometimes it's left, sometimes it's right. It can be many different things on many different periodic tables. So rather than remembering it as top or bottom or right or left or whatever, try and remember it as the massive number, the bigger number. It's also called the mass number because it indicates the mass of the atom. And if we think about the two things that have a mass, that's our protons and our neutrons. So the mass number is the sum of the protons and neutrons, the entire mass of the atom, everything that weighs something added together. To calculate then protons, neutrons and electrons, for protons, we just use the proton number, nice and easy. So for oxygen is 8. For electrons, we do the same because if you remember, our protons are positive, our electrons are negative, they need to be equal to keep the atom neutral as a whole. They have to equal each other to cancel each other out so that the atom doesn't become positively or negatively charged. Okay? And then for neutrons, we take the whole mass of the atom and we take away the protons, and that's how we figure out how many neutrons there are left. Okay? So for our oxygen, we have 16, the massive number. To take away the proton number gives us 8 as well. So it's 888 for all of those. The example in our homework, first thing to notice is, as I said, the mass number and the proton number have flipped. That can happen depending on what periodic table you use. But we know which is which because the mass number is bigger. Second thing to point out is that the mass number is not a whole number in this example. And that's because it's an average of all the masses. But all we need to know for now is that you round that to the nearest whole number. So 55.85 is rounded to 56 because you can't have 0.25 of a neutron. That doesn't make any sense. Okay, so it's 56, the nearest whole number. It can be up or down, nearest whole number. So work out protons, proton number 26. There are 26 protons. To work out neutrons, we do the sum 56, which is our rounded mass number, minus 26 protons equals 30 neutrons. Okay, that's how we calculate that. And then for electrons, as we said before, the number of electrons is always going to equal the number of protons because they cancel each other out. So again, that's 26. So the answer you should have is 26, 30, 26. Protons, neutrons, electrons. Okay? Moving on, another question that caused a little bit of confusion as to how many groups there are. So there are 8 groups, and the group number corresponds to the number of electrons in the outer shell. Okay, so we can see here our diagrams of lithium. Lithium has 1 going around its outermost shell, and it's in group 1. Chlorine has 7 in its outermost shell, it's group 7. The reason that there are 8 is because most atoms need 8 to have a full outer shell. So it's not just to do with the columns across, because I know there's 18 columns across, but it's to do with the fact that you need 8 to have a full outer shell. And all of the groups will follow the same pattern. I've highlighted the word most because obviously there's the examples. Hydrogen only has 1 in its outer shell, and then helium only has 2 because they've only got that first outer shell. So they're the only ones that don't follow the pattern. Every other one needs 8 for its outer shell, and that's why there's 8 groups. The answer, 8. There we go. Next, we're talking about why does boiling point change as you go down the groups? And in particular, we're talking about group 7. So melting and boiling points of the halogens, which is group 7, increase going down the group. As you can see from the graph, melting and boiling points increase. Why does that happen? Because the molecules become bigger. You can see in the electronic structures, they're getting bigger, there's more and more shells. And therefore, it's the intermolecular forces that become stronger. So it's not breaking bonds, it's not breaking bonds between atoms, it's between the molecules. So if you remember our our states of matter diagrams, and the fact that solids are regular packed together, liquids move around more, is to do with the molecules moving around, and the molecules separate from each other. It's not to do with breaking bonds between atoms. That's the difference, and that's why it's intermolecular forces, which is really important. Okay, intermolecular. So again, here we go. It's the bottom answer. The forces between iodine molecules rather than between the atoms that are stronger. Okay, that is a summary of the feedback from your homework. Well done to everybody. You all did really well, and I hope this can help you to make some improvements. Thanks, guys.